happy to give the first talk. Let's see. Alright, so I'm Christian. I'm a PhD student at the computer architecture group of my university, University of Twente in the Netherlands. And I'm going to tell you something about what I've been working on for the past 4 years, on and off, because I'm not working on my mandatory European project at Funky. So it's about compiling circuit descriptions that are based with just Haskell. So quick overview of what I'm going to talk about. I'm going to talk about what's CLaSH. Of course, the Implementor workshop, so I'll tell you about how the pipeline works. Something about the transformations that are happening inside. Yeah, something about structural versus behavioral and how that affects how you should look at your Haskell functions. Quickly, of course, we've been doing hardware in Haskell for a long time, but that's always been like mostly on the embedded domain-specific language side. We'll give a quick overview of why we're going to use CLaSH and Lava. So I brought the FPGA board with me to show actual running hardware. There will be a demo and some conclusions. So for those of you who are hardware design is not your everyday thing. Usually when people are designing hardware, they have like 3 things, or at least one of these 3 things. They usually have, they have this problem. It's mathematics. So those are all differential equations. So they need to discretize that, and usually they do it in MATLAB because when I talk to colleagues, not so much about they like the imperative style, but just because it gives them a lot of way to show the data. He said he would move to Haskell if he had the same plotting abilities as he has in MATLAB. That's maybe something for the community. I don't think it's very interesting. But anyways, and usually I have this schematic in mind, like how all the pieces fit together of your hardware. And sort of, yeah, it depends. But if you're like building a CPU, you usually just have the schematic and then some simulation in C. And this is what people then usually start with. And then comes the nice part. A lot of hard work. You have lint tools to check, your style of writing. You write test benches. You have 2 big screens with all the waveforms. What's happening on your simulation. Actually, they use a lot of verification in hardware industry, more so than in software. For certain in the ASIC industry. And and then maybe a bit of magic. And then they get like correct VCL, as in, everything is verified, but reasoning about the semantics of VCL is quite hard. So, people don't know, but it always looks correct, or at least all the test cases are working, all their properties are verified. So they have this correct VCL. And then I give it to the synthesis tool. So it can be a bit of a monster. I mean, there's this myth, and it's partially true, that your runs are not deterministic. So same code, press compile twice, different properties. So functionally correct, but non-functional properties might be different. Then once they're all finished, they look at this diagram. They get something like this, and then they had the original diagram they had in mind. Of course, I have to just pick these from Google. But the idea is that they look at the diagram here and there, and they see like, the synthesis tool didn't, accidentally throw stuff away, which actually happens sometimes. It messes up some output and says, this output's no longer needed, so everything that was driving that output, I can throw away. And suddenly your circuit becomes a whole lot smaller than you expected, but the synthesis bug. So, what is CLaSH? So I announced CLaSH, or the new version of CLaSH on Reddit, and it got picked up on Hacker News. So yeah, apparently I'm a winner now for most badly named programming language. Something to share with Go and Hack apparently. Although mine is worse because you can't type it in. But yeah, seriously. So what is CLaSH? Highlight. Yes. So what is CLaSH? So the acronym stands for Chaos Language for Synchronous Hardware, where Chaos is the name of my group. Yeah, I can skip that. It's usually when I go to hardware conference, I just tell people like I have this functional language, and I don't tell them about Haskell, because there's many people always in the hardware audience that remember Haskell and lazy evaluation and how bad it is, how bad it was. Sorry, and so they think, yeah, hardware is going to be bad as well. So I don't tell them it's Haskell, just show them like we have functional code and it maps structurally. Anyway, so I'm in the Haskell audience now. So what is CLaSH? It's a compiler that views Haskell programs as structural circuit descriptions. It accepts a semantic subset of Haskell. I'll come back to that. And what you get is very low level VHDL. I could output Verilog, but I'm not familiar with it, so it makes it easier to debug these things. So that's why I output VHDL, and in Europe it's what we usually use. So yeah, that's basically what the compiler does. So small example of CLaSH. If we want to model like sequential circuits, we use what Lava's been using. We use these streams or signals. So for example, here we have a simple circuit that does multiplication and accumulates. And so we have this register, which will be translated to a register in hardware. And we have this feedback loop that you see here. So we just use the recursive description to get feedback. And you see multiplication. So the above code gets mapped to the VHDL that produces the schematic you see at the bottom. And so yeah, you can already see a bit, what I mean by looking at it structurally. I mean, because we wrote register here, we get the register there. And we have multiplication, it gets the multiplication. So the thing is that the CLaSH will not, infer like the sequential hardware for you. You have to write down explicitly where you want to put your registers. There's other languages, that derive this. I think this gives you a cost model or operational semantics that's easy to read about, like how large is your circuit going to be, where are the registers, and things like that. But unlike Lava, we can also, process just pure functions. In this case, just a simple dot product, which is a pairwise multiplication and then a summation. And what we can see is that, because when we multiply these two vectors, they're all independent. They get mapped to 4 parallel multiplications also. Of course, you know this from Lava, but my compiler does the same. And then we get this adder tree because I use, a waterfall more because I use full length. So yeah, these are just 2 small examples of what CLaSH code looks like. As you can see, I use data kinds to for the type level naturals. So we're at the Implementor workshop, so I'll tell you, about the compiler, how it works. Of course, as many Haskell compilers these days, or variants of Haskell compilers, at CLaSH we uses the GHC API. And basically, we go from Haskell code to core. I have a custom set of optimizations enabled. Some aren't as beneficial for hardware as others. Also, like all the SCG and CMM customizations, I don't care about it. I have a core, For those of you that are intimately familiar with GHC, I don't run the core prep stage because it breaks up my integer literals into the integer constructor, which is annoying. Because I want normal integers, I don't want the representation that's used by the integer GMP library. Okay, then, so when we have the core, I translate it to my own core, where we don't have coercions anymore, because if you look at GC's core, there's coercions everywhere, and I kind of annoy it for my rewrite system, which has a very specific normal form. So, so yeah, I just get rid of them, and it works out most of the time. So yeah, then we normalize the core, because, well, I'll talk about that. Once it's in its normal form, it's almost trivial to convert it to a netlist, and then we pretty as VTL can be, pretty print it to file, and that's like sort of a global overview of the file. So my core is, basically GHC's old core for pre-coercions, and it's just system fh. Plus, because let bindings and case statements. So fairly, straightforward, small language. It reduces the amount of transformations that I need to, get to a normal form that maps well to hardware. So yeah, nothing you haven't seen. So yeah, I'll tell you, what it means to have this like a structural view on your descriptions. So when we have function application in our Haskell world and our core world, it will map to like an instantiation of this component on the hardware. So every time you call the function f, it becomes an explicit component in the hardware. And so this isn't always, so you have behavioral languages like I think it was 2000s was by Mycroft. Yeah, this language called SAFL, and there you would just, if you saw a function application, so a function would only be instantiated once as a component, and then every time you call the component, it will just add more arbitration and bus logic, so it can route everything to it. That's not what we do, because we want to get like all this fine-grained parallelism that's available in Haskell and get it as easily as possible. So every time you see a function, it gets a function application, it gets mapped to an instantiated component. Well, lambda binders just get translated. So if you have a component here on the right side, lambda binders just get mapped to input ports for your component, and the result of your function gets connected to the output of the component. So you can view then case statements. You can view them in two ways. You have, for example, if you have a product type, also sum of products. Like if you have a projection, it just means that when, for example, if you have a projection of a tuple, two wires come in from the tuple, and we just continue with one. So this makes, for example, so working with tuples, or putting in stuff into product types, getting them out, putting them in, putting them out. I mean, it's completely free in hardware. There's no overhead because it just becomes wires that the actual tuples take up no space. The constructor for the tuple takes up no space in hardware. It's the elements inside. And then an important part. So this is also new. So now we get to the subset. I cannot handle the effectful part of Haskell, and this is one of the reasons. So if we have a case statement on the left, all choice elements in Haskell map to case statements before. What I will do is I will run both alternatives in parallel, and then based on the subject of the case statement, I will choose one of their outputs. So if you had effectful code, things would go wrong because you would have an interaction between these parallel effects, even though the original semantics of Haskell would say the unchosen branch won't happen. So that's not what's going to happen in CLaSH. So that's why you can only run the pure part of Haskell. Yeah. So what does my normal form look like? It's basically you just get all lambdas. So I transform my port to a normal form. It's basically all lambdas that form the input ports. Then we get one big let rec statement, recursive let binding, where all values are in administrative normal form or applicative normal form. I forgot which one it is. I think it's administrative. And then the body of the let rec is always a simple variable, so it points to one of the bindings in the let rec. And it's completely monomorphic and first order. So also, again, this has some implications. For example, your main function, the top of your hierarchy, needs to be monomorphic and first order, so you can push everything down to make this complete hierarchy that's monomorphic and first order. And yeah. So for example, like if you have Haskell on the left, simple ALU, that's just either addition or multiplication. I get mapped to core on the right. And so this is not in the normal form that we want it to be yet. Then we go from the core on the left to my normal form. And here you can see the normal form. We have all lambdas at the top. Then one big recursive let binding. Again, in administrative normal form. So pulled out these operations, put them in there, and yeah, that's what it looks like. So yeah, it's very very straightforward. Now something about the design, the decisions about the compiler itself. I told you in the beginning, like when hardware designers, when they design hardware, and also in my group, my PWC group. They always think of this schematic, and the one they push on the synthesis play button, they want to see, the RTL diagram, and they want to see this schematic again. Only then do they believe that everything worked out all right. So it's very important to preserve the first order hierarchy, of your function hierarchy. So that's why I can't just inline everything. I need to do special. So that would be the easiest way to get rid of all the higher order functions. Because what we saw earlier is that if you have these, like if we have a function on the left-hand side and a component on the right-hand side, the values they travel over wires. And a function is kind of hard to represent, as bits because it can grow. And your hardware is static. You can get more or less bits whilst you run the program. So that's why it needs to be completely monomorphic and first order. Also within hardware, sharing is important. If you lose sharing, it means that you will duplicate. You will have more functions, and every function will get translated to a component. So if you lose sharing, you get a larger circuit, which is something you don't want. So the transformations try to preserve sharing as much as possible. There's like a standard, it's also used in GHC, transformation is like a case-to-case transformation. What you see here is you have one case statement. This will turn into like the multiplexer that we saw earlier, and then we have here the alternatives, another multiplexer. So we get now two multiplexers. One multiplexer feeding the subject of the other multiplexer, right? But then, so the case-to-case, which is sometimes needed, you get one multiplexer, and then for every alternative, another multiplexer. But this is like a potentially, you get like a bigger circuit because you get more multiplexers. So yeah, I still have to kind of figure out if this is always bad, because currently I only do this transformation when the subject of because I need to get rid of all the higher order functions, right? I only do this transformation case to case if these alternatives are higher order, so you can get rid of them. So yeah, I do case to case because then I have here the subject, which is in higher order form, I transform it to this, but usually now the stuff gets amortized away. So probably what's going to happen is I'll only have one alternative. Ultimately, because this E will be like a constructor with a function inside of it, but it's like a known constructor. So after this, I can probably do a case of known constructor, and get rid of most of the alternatives, and then, it has become cheap again. Yeah, something else that my compiler does. So, some things that must be primitive. What you can do in the compiler is just you have this file with all these templates inside. For example, for the register function, and what you can do then is you have to build it like this template. So whenever it sees the register function, instead of doing like this whole transformation process, it'll just pick up this template. So for example, what you can do is if you have different vendors from FPGA, you can put your own template for the same function. So it's sort of like a module system, but then for primitives. Because some of the synthesis tools from one vendor can work better with one kind of HDL than with the other. So you might want to change that. So that's what you're compiling on. So yeah, I promised. Why would you use CLaSH instead of Lava? We've been using for a long time in this community. Lava is sort of straightforward to implement as long as you take care of the observational sharing part. So it's been looked at for a long time and sort of handled. Also, my compiler has to deal with these recursive function, higher order functions, but yeah, in DSL, the Haskell's evaluation mechanism takes care of it, so you don't have to deal with it in a compiler. But yeah, so for circuit design, the most important reason why you would want to use static analysis on a normal compiler like CLaSH is because you want to have pattern matching as a way to specify the operations of your circuit. So if you look at an EDSL, you can use a case statement to sort of say, like, I don't want to generate this circuit or the other circuit, but you can't use the case statement itself to specify, the multiplexer. So yeah, if we have EDSL on the left-hand side, this bool is not observable because it's not a type signal; it doesn't generate the correct AST, so this doesn't work. And of course, on the right-hand side also doesn't work because true is not the correct pattern of signal, right? So yeah, those are technical. So it would be really nice if maybe somebody would figure out how to get pattern matching into EDSLs. I don't think it's been looked at much. And it's important because we want to use normal Haskell function again to program or to specify our behavior, but if they use internally case statement, it's not going to work. For example, I have a quick demo. Yeah. And it uses lens code, and probably it has some pattern matching inside, so you can't use those functions as part of your specification. Like, I have all these, these lens combinators here that might use pattern matching inside. I can use them with CLaSH. I couldn't use them with Lava. That's part of the specification of my circuit. All right, time for a demo. I forgot to start my synthesis tool, but anyway. So I brought an FPGA, and it comes pre-configured with stuff that's all been written in Haskell and compiled by CLaSH. Let's see. If it works. Yeah, I'll just show you. I hope.
Could you show us the board too?
Yeah.
Oh.
So let me turn on the. dark. If we had a monitor, it would work out better. But what you can see,
Turn off the light.
yeah, maybe we can turn off the lights. But, wow, so yay! This isn't really the best song either. Not in terms of damn it. Come back, please. Well, anyways, luckily I have my keyboard with me, and you can see what happens. So on the horizontal axis we have time, on the vertical axis we have frequency. You know, the color indicates intensity. So what it could do is, you know, so a keyboard driver, it communicates with the audio chip, the VGA display. You know, these are all, you know, control structures that you want to specify, you know, using case statements. Yeah, you know, I'm sort of running out of time, so maybe I can, you know, in the break show you more. But yeah, so it's all written in Haskell. What it could do is also filter the music, so you can either have, you know, filter out all the high ends of the music, but then it sounds really crappy. Or you can have like a cheap speaker effect, so it filters out all the bass. Yeah, and hopefully I'll get my Spotify to work again. Probably the hotel doesn't allow me to stream my music. So, of course, what isn't working? Important. Well, I deleted my corrections, and that was apparently a bad idea. Because now I can't support GADT pattern matching. So, for example, all my functions that work over vector, I have to make them primitive. So, like the map functions, it works out. I mean, you can do a lot of things. As long as you don't do like map with $, then things great. But if you do a map with +1, it works.
When you say work, what does that mean? What does not work look like?
It will complain that the output of your primitive is higher order, and then, you know, it has to assign that to a signal, and signals cannot be higher order. So that it will just give you an error like, I have this non-representable variable that I want to assign. Because normally I would specialize in higher order functions, but you can't specialize primitives. So. And like if we have, so what I said earlier, that if you have functions application, it gets instantiated. So if you have recursive functions, that would mean, you know, indefinite instantiation. So of course that's not going to work on hardware. So normally I would have to unroll all my recursive functions. But if you have a recursive function that doesn't reduce to can't be unrolled, no, it fails. So there's people working on this. So this is, let's say, scientifically not solved. This is technically not solved. I hope to hear one soon. And then we have the engineering part. The compiler is really slow. Let me see if I can start it up. You can see here sort of as very small, but you can see that, you know, just compiling this thing took like 228 seconds, and so that's quite a long time.
Why does it take so long?
We don't have Haskell.
No, it's slow.
No, it's so apparently when you're designing a compiler, you can't have optimization as an afterthought. You know. Yeah, they show you all these great tutorials about how you can do, how you can analyze a program, but these are like always like tiny library functions. And when I try to use all these techniques on my on the compiler, it's kind of hard to figure out where stuff goes wrong. I think it's partly in the binder library. Yeah, sorry. So for sure, it's quadratic in the size of the let bindings that I get.
Oh.
So that's quite bad.
So some time ago, I had a program to use 23 gigabytes of internal memory,
Mhm.
and I got it down to 2.3 as an afterthought. So I think it is possible.
Yeah. Yeah, I know.
We can look at it together.
It used to be even worse than this, so I've already improved it, but still it's slow. And I think it's to do with the library that I use for binders, but I'm not really sure. And I use an FPL stack, which I probably have to flatten. Yeah. Well, so one thing I want to do is for future work is inline higher order functions instead of specialization, because they only care about the first order structure, not the higher order structure. I want to support iterates, so I want to use a dependently type core internally. I don't know how to then have GHC's open type families and fit that into a dependently type core. That's what I want to do. Well, I use type nets, but those of you that work with type nets know that doesn't work well. I have a sort of ring solver. I hope to get it in shape for 7.10. My dissertation is due 23rd of October, so in November I will work on it. Actually, I talked to Adam Grundy, and so maybe we get like a better solver, not just ring solver, and make my compiler faster. Conclusions. You should all use the GHC API. You should use CLaSH when you care about pattern matching. Yeah, the third point, I didn't get to talk about it. You should stop using VGL, you should start using CLaSH. So, thank you.
Two questions already, one or two more.
So my question is about how you pattern match on subtypes. You said that you have to run basically both branches and then multiplex the output.
Mm-hmm.
So you cannot have impure functions because both side effects will run.
Yeah.
But there is one more very undesired side effect here. You are wasting energy on computing results that will not be needed. Why don't you just power gate the branches that are not selected?
Well, I could do that, but then I would need to. So that's because I keep my like the component simple, because then I would need to have like a signal going back to tell it it's enabled, yes or no. So because it's like a syntactic transformation, so I have to see a function as instantiated. It's not a context dependent instantiation.
You just cannot insert the power gate in your transformations. So what you need to do is to multiplex the inputs, which are the mode basically, and multiplex the power line.
Yeah.
Maybe we can take this offline and have time for one more question.
So I'm curious about this issue with GDTs you mentioned. So you're erasing the coercions, which seems fair enough, but then can you just treat it like any other algebraic basis? Are you using the types in the transformation?
Yeah, but I think I forgot why it didn't work out. And maybe I erased too much, or I threw away like the coercion patterns. Because you have like these coercion patterns in GADT, and I think I threw them away as well. But then still, you need to do some more stuff.
Great, let's thank Christian again.